I'm Dr. Brian Clayton, Director of Gonzaga University's Faith and Reason Institute. On behalf of the Institute's Executive Board, I welcome you to this evening's lecture, the first of two inspired by Father Spitzer's book, New Proofs for the Existence of God. For 9 consecutive years, the Gonzaga University Faith and Reason Institute sponsored a series of talks each spring under the general rubric, Physics and the God of Abraham. Our last such series was in 2009, when Father Spitzer was one of 3 speakers invited to address the Gonzaga and Spokane communities on the relationship between developments in contemporary physics and the existence and nature of the God of classical theism. The lectures this evening and next might then be considered a resumption and thus the 10th of that series following a 1-year hiatus. However, we are viewing these lectures as the inaugural events of a new project for the Institute, a project we are calling the Catholic Intellectual Tradition Project. The history of the Roman Catholic Church is also the history of a great intellectual tradition, a tradition of philosophical, scientific, and literary inquiry and exploration. It is an intellectual tradition that has long promoted the integration of faith and reason, and it is a living tradition that needs to be recognized and continued. The Institute intends to offer occasional lectures and programs that celebrate and contribute to the life of the Catholic intellectual tradition. The work of our speaker this evening is part of that tradition, and it extends the tradition in ways that are important for us as a Catholic university and as a people living amidst the civilization that the Catholic Church has helped to build and shape. Father Robert Spitzer of the Society of Jesus is no stranger to us here at Gonzaga. He is, of course, the immediate past president of the university, in which capacity he helped to guide and promote one of the most significant periods of growth in our university's history. Truly unprecedented. 2 years ago, Father Spitzer handed over to others the task of leading this university as he took up new opportunities and responsibilities. He is the co-founder and current president of the Majas Center of Reason and Faith, headquartered in Irvine, California. He is also the president of the Spitzer Center on Catholic Organizations, headquartered in Ann Arbor, Michigan, and the chief educational officer for EPI, the Ethics and Performance Institute, headquartered in Coeur d'Alene, Idaho. Many of us who worked with Father Spitzer when he was president here at Gonzaga had hoped that when he left that post, his schedule might get a bit less hectic and that he might be somewhat easier to reach by phone or email. Our hopes have been crushed. But I suppose that we should have known better. Father Spitzer's life has been marked by apparently boundless energy and contagious enthusiasm for the life of the mind and the life of faith. Father Spitzer received his BBA from Gonzaga University in 1974, his master's in philosophy from St. Louis University in 1978, his master's of divinity and theology from the Gregorian University in Rome in 1983, and his master's in theology and scripture from the Weston School of Theology in Cambridge, Massachusetts in 1984. He earned his doctorate in philosophy from the Catholic University of America in 1988 with a dissertation directed by Paul Weiss and entitled A Study of Objectively Real Time. Father Spitzer has held academic appointments at Georgetown University, Seattle University, and Gonzaga University. He has also published numerous articles in scholarly and popular journals ranging over topics as diverse as leadership, ethics, metaphysics, ontology of physics, and higher education. He is currently at work on 3 different books and has already completed and published 5, including New Proofs for the Existence of God, published last year by Eerdmans, which he will be signing for those who are interested after this evening's talk. Tonight he will address us on the topic, Was There a Beginning Before the Big Bang? Please join me in welcoming Father Robert Spitzer of the Society of Jesus. Thank you.
First and foremost, it's great to be back here. Great to be back in Zagland for sure, seeing all the students. And boy, I'll tell you, an exciting basketball season. And you know, I have to say, the university just looks wonderful, and I'm very, very happy to be here. As Brian indicated, Dr. Clayton indicated, I'm going to be speaking on this whole area of was there a beginning before the Big Bang? And so maybe I better contextualize that question. And before I do, I just want to say that if people are interested, I have a website where there's, if you like this material, if you know someone who needs to listen to this material again and again, there's free video casts on this website, 12 of them that go through some of the points I'll be making tonight. There's fact sheets on this website. All of it's free. All of it's downloadable. There's a Facebook where questions can be asked of PhDs in physics and philosophy. So if you're interested in this, you might want this website, Magis, M-A-G-I-S, reasonfaith.org. And I'll mention it after the talk. We do try to bring some of the points of the book down a little bit more to people who are non-physicists, non-philosopher level. Just very quickly, I want to give a context. And the context is what I'm going to call the standard Big Bang model. But before I do, there's an important caveat about looking at God from the vantage point of physics or science. And that is that there's an intrinsic limit to science. Science is inductive by nature. In other words, it moves from particulars to generalizations or universals. And because it does that, there's always kind of an openness to further discovery. Furthermore, in science, we really don't know, since we're moving from particulars to universals, right? We're not proceeding deductively, right? We really don't know whether we have discovered everything that there is to discover. And because we really don't know whether we've discovered everything that there is to discover, Stephen Hawking notwithstanding, who claimed on the Larry King show with me the other day that science had figured it all out. But he's the only physicist I know who believes that. And I don't even know if he really does myself. But the point, of course, is that yeah, they can make another discovery. So what does that mean? What it means is the best science can do is get to a rigorously established theory that has multiple data sets that becomes very, very difficult to deny. So you have a convergence of several data sets, not just in the evidence itself, but you have a convergence of data sets in the numbers themselves. And that makes for a very well-established theory, which we ought to really give assent to, unless there's a new discovery or there's a real reason that's discovered subsequently that would say that that theory needs to be modified or that we shouldn't believe it anymore. The Big Bang Theory is one such theory. It is a highly, highly rigorously established theory, and the standard Big Bang model today is held by most physicists. I mean, 99%. There are a few outliers, but most of them are most physicists are very, very much behind what we're going to call the standard Big Bang model. The reason I'll talk about a little later, there's a lot of evidence for it, and I'm not going to go into it comprehensively, but I'll give you an idea of what the evidence is. But I make all these claims about God, about a beginning, about the Big Bang model, etc., with always the caveat, one day something could be discovered which could force a modification of the model. There is one other thought, and the thought comes from a cardinal of the Catholic Church, John Henry Cardinal Newman. And he talked about an informal inference. He said the best science can do is come to an informal inference. And what he meant by that is you can get to a convergence of antecedent probabilities. In other words, you have a probabilistic conclusion, maybe you have a beginning from this set of data, a probabilistic conclusion from this set of data, a probabilistic conclusion from another completely different set of data. You have all these convergence, a convergence of these probabilistic conclusions, And that convergence actually does strengthen, makes more rigorous the theory or the conclusion that we draw. It makes it a little bit more immune, as it were, from modification or change. So with that caveat in mind, what's the standard Big Bang model? Standard Big Bang model essentially holds that the universe began, or at least the Big Bang occurred 13.7 billion years ago, plus or minus 200 million years. This is a very, very, very well-established fact from multiple databases. That theory itself, as we'll talk about it and expand it in just a moment, comes from a Catholic priest, a guy by the name of Father Georges Lemaitre, colleague of Einstein's, got his PhD at MIT, and then went on to work with Eddington and Einstein. And there was a problem in the general theory of relativity, which was well recognized way back in 1927. And the problem was what we call now today the radial velocities of extragalactic nebulae. In other words, the recessional nebula, they weren't, people didn't really know in 1927 whether these very, very bright nebulae were galaxies or something else. They knew there was something outside of our galaxy. But until Hubble came along and actually showed that these are other galaxies and other galactic systems, they were just classified as nebulae. And so these nebulae, you know, had a recessional velocity away from the observer, which was far, far, far too fast to be explained by Einstein's general theory of relativity if you assumed that the universe itself was in a steady state. So this Belgian priest, Father Georges Lemaitre, said, well, let's just be rather radical about this, and basically indicated, why don't we just assume that the universe is, it started off as a cosmic atom, and then it blew up, and then space and time began to stretch like a balloon. And of course, if you take a look at space and time stretching, you go, well, wait a minute, isn't space an empty vacuum? No, actually, Einstein's general theory of relativity actually showed that space is a rather malleable field. It can actually change its coordinate structure according to the density of mass energy in it. Literally, if you have a highly dense mass energy you know, centered in the space-time coordinate system, the coordinate system will collapse around that very dense mass. And you know, it'll spread out accordingly as you move away from it. Of course, the coordinate structures collapse, gets, you know, more and more and more you know, eased off, if you will. But next to the actual you know, mass density, space-time itself is changing its coordinate structure. Space-time was like a field. It was like a piece of elastic, as it were. It could do all kinds of things and adapt itself to the density of mass energy within it. It was in unity with mass energy. That was the theory of Dr. Einstein. What Lemaitre did was to show that if space-time had all of these properties, then it could stretch and grow just like a balloon. And it was Lemaitre, of course, who formulated that first kind of image of the universe starting off the size of an atom, 10 or even less, 10 to the minus 33 centimeters, almost like a completely deflated balloon to a particular point. And as you put all the various specks on the balloon, what you notice as you blow up the balloon is that all the specks on the surface of the balloon are moving away from each other, which is precisely what, of course, people were trying to explain at Lemaitre's time, and later what Edwin Hubble, the great American astronomer, actually proved. Every single galactic system and galaxy is moving away from every other galactic system, and the ones that are further away are moving away faster. We have to explain this, and of course, the explanation lies in the balloon analogy itself, where actually Lemaitre showed that the mathematics could explain the radial velocities of these extragalactic nebulae. Now, he presented this to Einstein. Einstein, in turn, looked at it and said, wow, the mathematics is excellent. The physics is preposterous. And he sent poor Lemaitre packing, literally, because he didn't want to believe that the universe actually was expanding, even though his own theory permitted the very stretching and expanding of space, which Lemaitre used as integral to his model. Eventually, of course, we know that a whole group of people, who I'll just talk about very briefly, came along and verified it. Edwin Hubble, Arno Penzias, Robert Wilson, and then of course the Cosmic Background Explorer satellite, the Wilkinson map, and isotropy probe, and so forth and so on. At the end of the day, the theory became one of the most rigorously established theories in cosmology and physics. Faith and science, I think, were integrated from the very beginning, not just in Lemaitre, but one can see that the moment that these discoveries were made, actually, the thought of a beginning was right in the midst of it all. And what I'm going to talk about in just a moment is the significance of a beginning in physics, because it's a very, very significant thing. But let's just get an outline. What do we think our universe is anyway? It's certainly not the universe of Dr. Newton. It's not infinite in extent, very probably. It might be in a certain sense with a certain definition of space, but probably not. It's not infinite in mass, and we'll talk about those numbers. It's not infinite in time if the Big Bang is truly the beginning of the universe, but it might not be. Was there a Big Bang before? Was there a period of, prior to the Big Bang? And was that period, did that period have to have a beginning? That's the question we'll have to answer tonight. But the key thought, of course, is right now, there were finite parameters everywhere in the universe. All of the infinities of Dr. Newton have been more or less removed. And today, what do we think of our universe? We think it's composed of 4.6% visible matter. So approximately 4.6% visible matter. And visible matter is luminescent. In other words, it emits light. It's electromagnetic, so it's got electromagnetic fields, and it does electromagnetic things, has electromagnetic properties. But that's only 4.6% of the matter energy in our universe. 23% of the matter energy in our universe is what's called dark matter. Dark matter doesn't emit light. It has no electromagnetic activity. As far as we can tell, it has no strong nuclear activity. As far as we can tell, it has no manifestations of the weak force. All it seems to do is, like a big old clump, interact with gravity. And that it does. It powerfully interacts with gravity, so it's causing a very strong force of attraction within the universe. The last component is what we call dark energy. And dark energy is not like dark matter at all. In fact, it has the opposite effect. Dark energy is like a field that attaches itself to that stretchable space-time field that Dr. Einstein predicted. But this field causes an exceedingly strong force of repulsion. And it is believed that it is because of dark energy, not only that the universe expanded and exploded, but it was also because of dark energy that the universe accelerated in its so-called inflationary period. 72.6% of the mass energy in our universe is dark energy, repulsive energy, like field attached to the space-time field. 23% dark matter, only 4.6% visible matter, able to do something, produce all the effects that we're seeing here in this room. What is visible matter like? What do we think about that? Well, there's approximately 10 to the 55 kilograms of visible matter in our universe. We don't want to postulate too much more of it, because that would, of course, mean that there is an imminent universal collapse. This would not be good for us. Just kidding. No. Actually, the dark energy would actually continue to pull it apart. But the key thought, of course, is there's about 10 to the 55 kilograms worth. That's equal approximately to 10 to the 80 baryons worth of mass. A baryon is a particle with the greatest rest mass. So it would be a proton or a neutron. So you have about 10 to the 80 protons and neutrons in the universe. And that 10 to the 80 protons and neutrons of mass is interacting through 4 fundamental forces, which will become important tomorrow night as we talk about anthropic coincidences. Well, what are those forces? I think all of you have heard of them before in one respect or another. The electromagnetic force, all of you have heard of, right? Everybody knows that electrons repel other electrons and attract protons and so forth at particular magnitudes, and they produce all kinds of luminescent electromagnetic activity from flashlights to cyclotrons. Second, strong nuclear force. I think many of you have heard about it at least. Right? Ever wonder why the protons stick together in the nucleus of an atom? Similarly charged particles should do what? Repel. Well, why in the world should you have similarly charged particles sticking together if they're supposed to repel? Only one explanation: there has to be a stronger force. A strong nuclear force is what it was called. A stronger force that, when very violent collisions occurred between protons and they got to within 10 to the minus 22 centimeters of one another, very, very small distance, then the strong nuclear force would take over and literally bind together these protons in what's called a fusion reaction, right? And a fusion unification. And when that occurred, all of that fine repelling electromagnetic force from the protons is pushed outward and goes boom. This produces the hydrogen bomb, and of course is the very reaction that is going on in our sun right now. The weak force is radioactive decay. It's the decay of particles. It also causes matter and antimatter to separate. But basically think of the weak force in terms of decay and radiation. And of course, then there's gravity. Gravity is the force of attraction, but of course the force of attraction between particles is really not a force at all. As Einstein discovered, it's the coordinate structure of space and time. A collapsed coordinate structure of space and time due to a lot of mass energy is precisely what will cause all of the effects, explicable effects of gravity without appealing to a force. That, in a nutshell, is our standard Big Bang universe. That's what we think we live in. It's not infinite. It's pretty big, but it's not the universe of Dr. Newton. It's very much the universe of Dr. Einstein. Okay, so let's just really quickly zip through, what happened really, and why did people actually believe that the Big Bang Theory was true ultimately. One of the reasons is because of the work of...
I'm so sorry to interrupt, but I want to start your PowerPoint.
Oh.
For you. It didn't come on.
Technology.
Okay.
The electromagnetic force is not operating appropriately.
Now we're good.
See if you can skip all the way to Edwin Hubble. Past all that info. Sorry about that. So, we have Lemaitre proposing this theory, the mathematics of which is very, very explicative. And then you have Edwin Hubble, the American astronomer on Mount Wilson, very close to where I now live, makes these discoveries of the red shifting of these extragalactic nebulae, which he later discovers through both the telescopes at Mount Wilson and Mount Palomar are truly galaxies out there. They're not just nebulae, they're not just unknown things, they're other galaxies, thousands of other galaxies. In fact, millions and trillions of them. There are 10 to the 11 galaxies in our universe, constituted by 10 to the 22 stars. So there's lots of galaxies out there. But the point is, they're all moving away from each other. And this would seem to indicate what could possibly be moving the galaxies away from one another in a uniform way. And it's a precisely uniform way. Such a uniform way that it is describable by a single constant, not surprisingly, called the Hubble Constant. What is the only possible explanation for everything moving away from everything else in a precisely uniform way? It has to be that the space-time in which the galaxies are immersed is actually growing larger and stretching and pulling the galaxies along with it in its stretch. And that's precisely what Hubble proved, and the establishment of the Hubble constant was heralded, literally heralded, as a proof of the so-called Big Bang Theory. At the time, it was still called the theory of the cosmic atom, what Lemaitre had named it. But then Fred Hoyle, a famous atheist who later converted to theism because of the, we'll talk about it last night, because the carbon molecule, dubbed it, that's the Big Bang. So in a very sarcastic move. It later got verified by Arno Penzias and Robert Wilson. I live pretty close to Arno Penzias. I've just completed a documentary for the Discovery Science Channel. And in that documentary, we feature Arno Penzias, who discovered this background radiation of the Big Bang. Essentially, what that is a radiation that's uniformly distributed in the universe. And the only way you can get a uniformly distributed radiation is literally if that radiation is present at the very beginnings of the universe and expands uniformly, like this peanut butter on a balloon almost, expands uniformly along with the stretching of space itself. Actually, Penzias and Wilson discovered it in 1964. Obviously, they won a Nobel Prize for it, most important cosmological discovery. But what was it? It was the leftover remnant, the radiation remnant of the big explosion, this Big Bang that occurred, that set the universe and its stretch into motion. And that, of course, this leftover radiation, this echo from the Big Bang, gets stretched out uniformly, and that has been verified again and again and again. There is also the Cosmic Background Explorer satellite, which refined all of the properties of the cosmic microwave background radiation, the CMB radiation. And finally, of course, there is the Wilkinson map anisotropy probe, which, of course, refined it even further. As I said before, there is hardly a physicist in the world that does not adhere to the standard Big Bang model. It is so well corroborated. 13.7 billion years ago, there was a huge explosion of a mass energy system that essentially blew into what we now call 10 to the 55 kilograms of mass energy, rest mass today. And it has a variety of properties we will be talking about. It's equivalent to about 10 to the 22 stars in 10 to the 11 galaxies. And as I said, it is quite rigorously established. What is the whole point? The point is, was the Big Bang the beginning? That is the point. There is a reason to suspect that it might not be, because when the universe was moving from 0, a singularity, to 10 to the minus 33 centimeters, which is a very small amount of motion, but it would have had to have been in another kind of state. It couldn't have been in a state describable by the general theory of relativity. It couldn't have had a space-time field and then mass in it. Instead, gravity has to be strongly interacting with those other three forces I told you about, the strong nuclear force, the electromagnetic forces, and the weak forces. And it has to be interacting not through a space-time field, but as a real strong force, a force of gravity, which many physicists have tried to unify together in an area called quantum cosmology, which is an exceedingly complex area. There's two very well-known theories that have attempted anyway to come up with comprehensive theories about how you could unify gravity with the other three forces. One of them is string theory, and it's cousin M theory, which is 11-dimensional string theory, which has higher dimensional space, and we'll talk about that later. Another one is called loop quantum gravity, which is put together by Ashtekar and others, which is basically a minimizing of general theory of relativity. It doesn't really require higher dimensional space, doesn't require strings. It basically is an extension backward into time of the general theory of relativity of the space-time field through a series of microspins and things of that nature. But these are the only two theories that really have a comprehensiveness. Those are the two competitors. They're actually quite different in many ways. But the point is, that's how we would explain it. But because there is that period from 0 to 10 to the minus 33 centimeters, because there's also an inflationary period in the universe, it is possible that perhaps the Big Bang was not the beginning. Now, if you took a poll of physicists today, I'd probably suspect that 50% of them would tell you right off, you know, as Polkinghorne would say, you know, higher dimensional string activity as a prior period, rubbish. It's all rubbish. You know, other physicists will tell you, and this is an Arno Penzias example, well, that's just a theory which can never be denied. You can just keep changing it and changing it every time you find a problem with it. I can prove to you, you know, that elephants like ice cream. How would I do that? Well, there's elephants in zoos, and there's ice cream in zoos. I put the ice cream in front of the elephant. I say, have some ice cream. He doesn't eat it. I forgot to tell you, on Thursday afternoons, elephants don't eat ice cream. And that's right off the, literally right off the documentary. So, I mean, that was Arno Penzias. He just, you know. But the key thought, of course, is, so that's one group of physicists, but there are another 50% of physicists who remain open to the option that there was a prior period. In other words, a period prior to the Big Bang. The Big Bang was not the beginning of the universe. The universe is older than 13.7 billion years. And we'll talk about two major theories for how these physicists are proposing the possibility of this prior period. Before I actually say them, I just want you to know there's not a scintilla of evidence for them. There's the possibility of them because of quantum cosmology and inflationary theory, but we don't have any evidence of these prior periods right now. That's why the physics community is so divided. But what are they? The first, many of you have heard about, is the oscillating universe. Expanding and contracting and expanding and contracting. And literally expanding and contracting up to an infinity of times. In other words, it's expanding and contracting. And if it expands and contracts, if it's been expanding and contracting an infinity of times, then the universe is an infinity years old. And so you can get out of the beginning. Second one is called the multiverse theory. Multiverse theory essentially comes from quantum cosmology. The collapse of a false vacuum in an inflationary condition actually allows for a universe to burp out, as it were, a bubble universe or a pocket universe. And so, of course, if you have a multiverse condition, and we'll talk about the multiverse in detail tomorrow, but if you have a multiverse condition, essentially it could keep burping out, I mean, theoretically, hypothetically, it could keep burping out bubble universes for a long, long, long time. And each of those bubble universes could actually have a whole new set of constants. And as we talk about fine-tuning tomorrow, this becomes a competitive theory with the so-called design hypothesis. But those are the two contenders. The multiverse theory, the oscillating universe theory. Now, the oscillating universe theory has gone through a whole lot of iterations. There's a fundamental problem with it, and I'm just going to talk about oscillations right now, and I'm just going to talk about kind of how the theory has developed, and I'm going to talk about it under the rubric of entropy. So if we could just flip to that triangle slide where entropy is kind of highlighted. There are two basic data sets that seem to indicate that even in an oscillating universe theory, so prior to the Big Bang, there were all these other oscillations of the universe. Or prior to the Big Bang, we're just one bubble universe amidst myriads and myriads and impossible infinity of universes in a multiverse. You with me? Sort of? You got two major contenders. Okay. The multiverse, the oscillating universe. The thing is theoretically they could go on infinitely, but they're two big data sets that indicate that they do not. The first data set I just want to go through very briefly with you is the entropy data set. The second set I want to go through with you is space-time geometry proofs. Both of them suggest that these two theoretical, hypothetical, speculative scenarios of the multiverse and the oscillating universe, even in string theoretical higher dimensions, must also have a beginning. They cannot have proceeded eternally back in time. Starting with entropy. The law of entropy, as Einstein once said, is the one thing that will probably last forever. All theories may change, but at the end of the day, the theory of entropy will stay with us. Why did he believe that? Because he believed that entropy was an irreversible process on the basis of mathematical probabilities alone. What's entropy? We start off essentially with complex energetic systems, and these organized complex systems of energy can actually do work. You need complex organized systems of energy to do work, to do something, to maintain life forms, to allow life forms to develop, to have complex systems arise, to permit schemes of recurrence. You gotta have some usable energy. And usable energy comes in the form of what we're going to call complex organized systems. But the theory of, or the law of entropy, the second law of thermodynamics, holds that essentially all of this will break down. All complex organized systems, as they perform work, will eventually become more and more and more disorganized, more and more and more random. And eventually this more disorganized and more random, occurrence will eventually turn into what we call thermodynamic equilibrium. It'll literally turn into a system incapable of work. It's completely random. It's like the cosmic microwave background radiation, which is just some warmth out there, right? That's all. It can't do anything. It's really random, disorganized, unworkable. Now, this is an inexorable process for mathematical statistical reasons. What? Organized energy and complex organized energy is far more improbable than random, disorganized energy. Look, you have a pool table, and there you have a finely racked group of pool balls, and they're all together. You take a cue ball, shoot it at the racked balls, they scatter randomly across the table. You go, so? That's to be expected. But wouldn't it be unusual if you shot the cue ball at the 10 ball, which hit the 7 ball, which hit the 8 ball, and then blah, 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 and it turns into a racked, organized, complex group and spits the cue ball out at the end? You would say, that was unusual. And so it is. Basically, disorganized systems, right, are highly probable, organized ones improbable, and of course, as Einstein maintained, and as well as Fermi and so many others, this process is an inexorable, irreversible process. Einstein himself said, If energy in our universe is finite, so you have a finite amount of workable complex energy, and time has been infinite, then you should have absolutely no workable energy in the universe right now. You would have what's called maximum entropy, maximum cosmic microwave background radiation pushed down to microfractions of degrees above Kelvin. Unable to do anything. That's not our universe at all. Our universe, as a matter of fact, has a very low state of entropy. Not a high state of entropy. Which means either it hasn't been around for an infinite amount of time, or entropy got reset. Is entropy reset in an oscillation? That was one of the things that Richard Tolman tried to answer a long time ago. It's called Tolman's limit. I don't want to get into that. You can read about it in the book. The main thing, though, is the equations of Jacob Bekenstein seem to indicate that that is not the case. What seems to be the case is that when the universe goes into a collapse phase, instead of entropy resetting, as it were, entropy goes up enormously. 10 to the 800 times. As the universe collapses and goes toward a singularity, it begins to get into a state called BKL chaos. And when it gets into the BKL chaos state, the entropy during that state is rising enormously and enormously. If Bekenstein is correct, then a universal collapse would accelerate the process of entropy going up. And so right now, unless you can really find a theory that explains how entropy can reset, it does not seem that an oscillating universe, right now, it does not seem that an oscillating universe could have oscillated an infinite number of times. There are two other inconvenient facts. Dark energy. Remember that repulsive force that causes the universe to expand? Well, we know this cycle, I mean, unless you can get rid of the dark energy, and there are some people who are really trying desperately to get rid of that dark energy, but it's not working. Theoretically, it's not working. In fact, it's just the opposite. Try as we might to get rid of dark energy, it seems to not only persist, but to be our little boogeyman. Which means our universe is very, very, very unlikely to collapse. It will continue to expand until it reaches thermodynamic equilibrium approximately 26 billion years from now and just dies what's called heat death. But what about those other cycles? How could you get the other cycles to collapse? You got to get rid of the dark energy in the cycles. And then again, you got to have the magic crafty ways. Make it go away and then make it come around. Deus ex machina, God in the machine, removing and taking away natural forces. Does not sound that good theoretically from the vantage point of naturalism. In a discussion with Leonard Mlodinow, by the way, who, you know, he and Stephen Hawking ignore all this evidence in the grand design, does really irk you, because there are far more errors of omission than commission. And we're talking some really high-end physicists here who have developed these theories. There's just no reason to ignore this evidence. I mean, it's out in the best literature of physics, but that's another thing. I guess the 2 points I want to make from entropy from that data set is simply, number one, if the universe is infinite and has finite energy, then the universe has not been around for an infinity. Does it seem possible that in an oscillating universe you're going to have an entropy reset? Doesn't seem very likely. BKL chaos and the equations of Bekenstein seem right now to rule that out. And then you have the dark energy problem on top of it, getting into the mix with the oscillating universe theory. Not that great. Does entropy proceed in a multiverse? That's been the big question. It seems so. And the reason you say, well, wait a minute, you can't even visit the other universes, let alone the multiverse itself. How can you be so sure, Spitzer, that there's entropy in a multiverse? Because entropy is essentially a statistical theory. It simply says that there are far more random possibilities, right? The probability of randomness and disorganization far, far, far exceeds the probability of complex organization. And for that reason, many physicists today hold that entropy as a statistical theory, not just a thermodynamic theory, but as a statistical theory, would have to apply to a multiverse itself, because there seems to be an intrinsic breakdown in every single complex system toward greater and greater disorganization and randomness. Enough said. So the multiverse theory and the oscillating universe theory, even though we haven't seen a prior cycle, even though we can't in principle visit another universe or the multiverse itself, would seem to have a limit. You sort of hanging in there? A beginning. It can't be eternal into the past. There's a second big data set. It's not like entropy at all, but it leads to the same conclusion, and it's called space-time geometry proofs. There are three of them I just want to talk about today. The first was put out in 1993 by Arvind Borda, an Indian physicist who's now at the Kavli Institute at the University of California, Santa Barbara, and Alexander Vilenkin, a Russian physicist who's now at Tufts University. The two of them got together in 1993 and published what is now called the first space-time geometry proof for inflationary model universes. Our universe is an inflationary model. In other words, we have dark energy in it, the universe is inflating, we had a period of high degree of acceleration. There are a couple of physicists like Roger Penrose who challenged the inflationary period, but by and large, the inflationary theory is standing up to scrutiny very, very well. The guy who thought of that theory is an American physicist by the name of Alan Guth. And he will factor into this whole scenario prominently in just a moment. But here's the thought at hand. The thought is Alexander Vilenkin and Arvind Borda get together and they formulate a proof which shows that every inflationary model universe and multiverse, and the inflationary model universe or multiverse. And why multiverse? Because all multiverses must be inflationary. In order to have the collapse of the false vacuum, what permits a bubble universe to burp out of that condition is the inflationary dimension. If you didn't have inflation, you couldn't have a multiverse. So what they showed in 1993 was if the universe met 5 different conditions, or any multiverse met 5 different conditions, then for all intents and purposes, you would have to have a beginning. Now, that proof is nicely stated in Physical Review Letters in 1993, highest peer-reviewed journal in physics, right? And so out it comes. Ooh, boy, everybody reacts to that pop. And then, of course, they found, Vilenkin and Borda found an exception to their proof in 1997 called the weak energy condition. Now, the exception doesn't seem to apply to our universe at all. It's just a theoretical exception. In other words, how can I break out of these 5 conditions of these proofs to make sure that there would be at least one inflationary condition that didn't have to have a beginning? And they found one which was a very, very, very strange way of utilizing de Sitter space with quantum cosmology to kind of pull the whole thing together. But Alan Guth, the physicist at MIT who invented inflationary theory, came along and he said, you know, I do not consider this exception to be applicable to our universe or to any multiverse to which it could be connected. So essentially, Guth disputed the importance of it. In fact, he said, I consider the exception to be of no importance. The proof of Arvind Borda and Alexander Vilenkin stands as is. Then in 1999, Guth himself approached it from a different point of view. What he did was a comprehensive study of every generatable inflationary model he could get, ones that had been done in the past, ones that he himself generated, and came up with this astounding conclusion in 1999. Every single inflationary model that we generate, try as physicists might to find a single model that does not require a beginning, they have been unable to do so. Comprehensive modeling of our universe or any multiverse to which it must be could be connected, would have to have a beginning. It can be eternal into the future, he said, but it cannot be eternal into the past. That's very interesting. Then in 2003, the three of them get together at MIT. So Arvind Borda, Alexander Vilenkin, and Alan Guth get together and surprisingly come up with a very important theorem called the Bvg Theorem, the Borda, Vilenkin, and Guth theorem. Very creative. This theorem is exceedingly important because it has only one condition. So this is published in 2003 Physical Review Letters, and you can get the basic points of it from the quotes here in the book. Only one condition, that the average Hubble expansion of any universe with any physical dynamics. So change the conditions. We, in fact, says Vilenkin, we did not even assume that space-time was described by Einstein's general theory of relativity, etc., 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 etc. We made no such assumptions. The only assumption or condition that had to be made was that the average Hubble expansion be greater than 0, no matter how small. Now, what does that mean? The Hubble expansion is just the rate of expansion of the universe. So what you basically need is one that is greater than 0. You can't have one less than or equal to 0. The way the proof essentially works is this. As one goes further and further into the future, because of the expansion of space, and then the expansion of the previously expanded space, and then the expansion of the previously expanded space, as one goes into the future, all the recessional velocities decrease in the universe. They decrease because all relative velocities inside the universe, they're fighting, as it were, the expansion of space, right? They're fighting the continuous expansion of the expansion of the expansion of the coordinate system of space and time. And so recessional velocities and relative velocities in the universe decrease. But that means if you go back into the past, what winds up happening is they increase. So 1 billion years ago, 2 billion years ago, 3 billion years ago, etc., they would have to be getting faster and faster and faster and faster until all relative velocities of all energetic reference frames, we're not talking about is there a tachyon which can exceed the speed of light. All they're saying is every single electromagnetic system which is regulated by the speed of light constant, which is their absolute limit, all relative velocities would literally be at the speed of light, an absolute limit, and you can't go back any further. They have had this published since 2003. What's the overall point? The overall point is that it does seem that every inflationary model universe that has a rate of expansion greater than 0 has to have a beginning. Oh, by the way, it's not just universes. Every multiverse would have to have the same thing. And not only every multiverse, but every string theoretical higher dimensional space multiverse. I mean, Arvin Borda and Alexander Lincoln and Alan Guth extend it to all string theoretical models. And furthermore, it not only applies to every oh, by the way, remember, every multiverse must be inflationary, so every multiverse by definition must be subject to the Bvg theorem, and as subject to the Bvg theorem would have to have a beginning. And furthermore, it applies to oscillating universes. What they discovered was all you need is an average Hubble expansion greater than 0. So in other words, all you need is to start the entire process with an expanding cycle. If one cycle essentially has an average rate of expansion greater than 0, it doesn't matter how many collapses and expansion. The average Hubble expansion in that case would be greater than 0 and would be subject to the Bvg theorem. Now, there are a lot of people really worried about this theorem. In 2006, Vilenkin came out and started pushing people and basically made this incredible declaration to conceive of any system, which is any universal system or multiversal system, which has an average Hubble expansion greater than 0, as one not having a beginning is impossible. Physicists don't use that word very often. They don't. But the nature of the proof is a single condition. And that makes it very vexing, makes it hard to get out of. Very hard to get out of. Just leave it at that for just a second. Now, if you take a look at this massive amount of data from entropy and this massive amount of data from space-time geometry proofs, including the 1993 Borda-Vilenkin proof, which is still valid today, having 5 conditions, the 1999 Alan Guth comprehensive study and modeling of inflationary model universes, which have to have a beginning, and also the 2003 Borda-Vilenkin Guth Bvg theorem. If you take a look at that and you combine it up with the entropy evidence, boy, it's starting to look really probable. That even if you had a prior period, a multiversal period, an oscillating period, a higher dimensional space string theoretical period, a loop quantum gravitational period, even in all the speculative scenarios you can find, it would seem to be that theoretical multiverse, that theoretical oscillating universe, or our universe itself would have to have a beginning. Now, there are some physicists who are trying to get out of this. There are a bunch of guys who, I talk about in here and redress the problems, who are busy trying to deconstruct time. There are other people who are saying, no, there are other universes on the other side of de Sitter space and so forth and so on, that do all kinds of other things that can get us out of it. Even the agnostic Sean Carroll says, oh, stop. He says, stop, because all you see, low entropy is so improbable, right? And we'll get to this tomorrow. I mean, literally, Roger Penrose calculated the odds of low entropy at our universe, at the Big Bang. It's 10 raised to the 10 raised to the 123 to 1 against low entropy. That's a really big number. I mean, that's like 10, and then in the exponent, a 1 with 123 zeros after it. In the exponent. If you put every zero at 10-point type, our Milky Way would not hold this number, our galaxy. That's like saying you gave an order to a monkey, type the complete corpus of Shakespeare in 2 weeks. I'm coming back. By random tapping of the keys, the monkey begins furiously tapping. And then, of course, you come back 2 weeks later. Oh, Hamlet and Macbeth and Richard III. And it's all perfectly done. That's highly improbable. And dead it is. It's not likely. Now, remember what I said about Jacob Bekenstein, 10 to the 800 power, every time you have a universal collapse? So you take the 10 to the 10 to the 123 and you start multiplying it by 10 to the 800, 10 to the 800, 10 to the 800, and that quantity times 10 to the 800, that quantity times 10 to the 800, and you keep going back, back, back for every single cycle. Just keep going. And it gets so much more improbable for each cycle that finally the agnostic, Sean Carroll finally says at the end of it, he says, this would seem to imply infinite fine-tuning without any good reason. What's the point? The convergence of the data from entropy and the convergence of the data from space-time geometry proofs makes it not only reasonable and responsible to believe that any theoretical or hypothetical period configured by a multiverse or an oscillating universe, even in string theoretical higher dimensional space, would have to have a beginning. Despite all the attempts to get out of it, it just still stands like a sore thumb. Why are people trying to get out of it? Why? Because a beginning in physics is a big deal. Why is it a big deal? Because it's the actual beginning of physical time. Time in physics is something. It has real effects in nature. It is not merely the Aristotelian thought of the measure of motion, which could be at least seen to be something subjective or something measurable in a motion. It's more than that. It's a physical thing connected. It's like a non-contemporaneous continuum, like Bergson envisions it like a cosmic memory, if you will, where you have a non-contemporaneous continuum held together by some kind of cosmic memory, as it were. But it's something. It's something. And it's linked to a contemporaneous continuum, which is space. And that space-time continuum has real physical, natural effects. What's so important about this? If you say there was a beginning, you're saying there is a beginning of physical time. If you're saying that there was a beginning of physical time, then the beginning of the universe is the point at which it and its time came into existence. If we may speak of prior to that moment, which we really can't in terms of physics, you'll have to use some metaphysical time here. Then prior to that moment, the universe and its physical time was nothing. Now, Stephen Hawking and I, we disagree on this. And Leonard Mlodinow too. I would insist on this from the very beginning, notwithstanding the fact that Stephen Hawking has a much higher IQ than me. Nothing is nothing. From nothing, only nothing comes. Nothing is not a vacuum. You can have more or less of a vacuum. You can't have more or less of nothing, because nothing is nothing. Space-time is not nothing. Even empty space-time is not nothing. Space-time is dimensional, orientable. You can have more or less of it, but you can't have dimensional nothing, orientable nothing, more or less nothing, because nothing is nothing. Now, if nothing's really nothing, then what can nothing do? I mean, really? Nothing. Nothing, as Parmenides, or as all the Parmenidians said, the Eleatics, from nothing, only nothing comes. Because nothing can't do anything, because nothing is nothing. So you say, well, what's so important about that? Well, if the universe was nothing, and therefore it couldn't do anything to bring itself into existence, because nothing can only do nothing, then something else has to bring it into existence. because it could not have done that when it was nothing. Which means that if there's a high probability of a beginning, there is also a high probability of some transcendent force outside of our universal or multiversal space-time asymmetry, which brought the universe into existence, including physical time itself, in a single moment at which time comes into being coordinately with the universe. There's a likelihood of something really big out there. And it's really powerful. Now, I say all of this with the caveat that I said before. Gosh, we could discover something about entropy that we don't currently know. But right now, there's no such evidence. We could discover something about the Bvg theorem. We could discover something about physical time. We could discover something about a lot of things that we don't, and that could change everything. Or maybe it would cause a modification. But right now, the interesting thing is, and tomorrow night we'll take a look at a whole different set of things called fine-tuning arguments. The key thing right now for tonight is that you have two different sets of data from entropy and from the space-time geometry arguments, all three of them, the 1993, the 1999, and the 2003, that seem to converge both numerically and physically on a single conclusion, that even a pre-Big Bang period would seem to have a beginning, all things remaining the same in physics as we view it today. I do not think it is possible to get out of this by a string theoretical configuration, because Bordovoulenko and Guth themselves applied the theorem to string theoretical configurations, both for oscillating and multiversal symmetries. So for all intents and purposes, it seems at least likely now that there might be something really, really powerful out there that caused the whole thing to exist. Tomorrow night we'll talk about whether or not such a thing is truly intelligent, or in Hoyle's converted words, a super-calculating super-intellect. But for the time being, suffice it to say that this seems to sound like God. Does this converge with philosophical proofs like Hilbertian ones? Yes, it does. Does it converge with all kinds of metaphysical philosophical proofs? Yes, it does. Philosophy of mathematics proofs? Yes, it does. I think, quite frankly, we live in an era today where the evidence for a beginning of the universe, the evidence for God, is perhaps more prolific and more coordinate and more convergent than at any other time in history. It does give one pause. Why am I out there debating Dawkins and Hawking and Mlodinow? Why is this going on? And I just tell you this, you're students who know well enough. There are far more errors of omission than commission. You can't leave out entropy data. Stephen Hawking himself is a space-time theorist. He knows the Bvg theorem. He's read about it. All of his physicist friends are writing about it and trying to get out of it. How can you not mention this in your book? I just think we have to take a look at that and say, in all honesty, what do we seek as rational people? The most complete explanation that considers the most evidence and theoretically converges that evidence to its natural conclusion. And I would submit that the evidence today does favor a theistic explanation. Thank you very much. We have plenty of time for questions, and I'll let Margaret or Brian moderate those.
There's a question here.
Right. Do people want to use this mic?
Not away from you with the use of powers to the raised powers. You said that there were 10 to the 11th galaxies populated by 10 to the 22nd stars.
Mm-hmm.
Would you estimate that to be really greater than the number of grains of sand on the beaches of the world?
Would I estimate it as greater than the number of grains? You know, I didn't do the sand count, but 10 to the 22 is pretty big. I would probably say it certainly rivals that number. That's an awfully big number. But the particular figure I was pointing out was the Penrose number, which is 10 to the 10 to the 123. But yeah, could be.
So given that the naked human eye, when Moses was writing the Pentateuch, and he said that God had said that the people of the Jews would be greater than the number of grains of sand on the beach, talking about the forefathers, Abraham. And at the time of the naked eye, you could see about 1,200 stars, 1,300 stars, something like that. Then is it reasonable to assume that the writing of the Old Testament was truly divinely inspired, because until we started having a telescope, nobody knew that there were more than 1,200 or 1,300 stars you could actually see with the naked eye? Is that a reasonable assumption?
Well, I mean, from a hermeneutical perspective, you have to be a little careful with numbers in the Old Testament, first of all. And also trying to attribute a scientific explanation to a biblical author. Catholics have an encyclical called Divino Afflante Spiritu. It was written by Pope Pius XII. I think it was back in 1941 or so. But in any case, in that he says basically this, that what we want from the Old Testament and New Testament scripture are the truths of theology that are pertinent to our salvation. And then he explicitly says a lot of what's going on in terms of the cosmos and the physical unraveling of the cosmos, a lot of that is not really pertinent to our, I mean, it's very nice to know, but in as much as it's not pertinent to our salvation, we don't want to sit there and try to make the biblical author mean something literally. Now, from the vantage point of, the Genesis story, for example, honestly, I do not believe that God gave a scientific account to that poor biblical author in the 6th century BC. First of all, he really didn't have any grounds to understand scientific method, experimental methodology, quantification systems. Heck, he didn't even know the calculus. I mean, it would have been impossible, honestly, to understand that. What was his problem? His problem was a theological problem. There's rival myths out there, and the rival myths have many gods. And the moon's a god, and the sun's a god. And furthermore, the gods are capricious and unjust, and they treat human beings like they're nothing, and they toy with them, and so forth. And matter is evil. So he's got to redress the whole thing. And here's where I think inspiration comes in. It's really important for us to know that there's one God. And I think it's really important for us to know that the sun's not a god and the moon's not a god. I think it's really important for us to know that God doesn't toy with us, and that God is just. And I think it's really important for us to know that we are made in the image of God with the dignity of God himself. I think that's really important. I think those are truths for salvation. But do I really think that he meant 7 days in the sense of a solar day, which would be defined by a rotation of the earth prior to the time there was an earth? No. No, I don't. I don't think that. And I think trying to read, so what do I think? I think, apropos of your point, there are a lot of things which are really uncanny in Scripture. I mean, for example, let there be light. How in the world did he figure that one out? But that's right. That's the first step. Boom. A lot of light, a lot of energy. How in the world did he kind of unfold the sequence, right? I don't know, but a lot of it is strikingly right, you know? But you don't want to say it's science, because science does have its own methodology. So I guess I go with you to the point where I say, boy, that's really strange. That's very uncanny. I don't know how he got that information, but it's really interesting. But I wouldn't try and make it like a scientific argument, because then what happens is you kind of get into, you know, forcing the poor biblical author into being a scientist, which he really wasn't, to be honest with you. By the way, he had to operate according to the categories of his time, too, you know, which are very different from scientific categories. But so, yes and no. How's that for an answer?
There's a question up in the balcony over here.
Thank you very much, Father. You imply that Hawking no longer subscribes to a beginning, the Big Bang, and I'm not sure if that's truly his position, but if it is, why does he hold that? Why can you speculate on why he would omit those data that imply otherwise?
Well, you're right. I mean, does he come out and say definitively there was no beginning? No, but he tries to imply it. He's had 4 shifts in his life. He's gone from, gosh, you know, when he was down at Caltech, he used to go down to St. Phil's Church. You know, so he's had a religious phase of his life. He's had a kind of a theistic, non-religious phase. He's had a agnostic phase. Then he went back to a theistic phase in baby black holes. Then he's back now to a kind of a more agnostic phase. It's very, I mean, even in brief history of time, you know, what breathed fire into the equations of physics that they might do? That's the first question I asked Hawking and Mlodinow on the Larry King show. What happened? You know, and I would suspect that maybe the agenda is not physical. I could never say that for certain, right? But maybe there's some other agenda. And there have been some very comprehensive studies done of agnosticism and atheism. And the foremost reason for agnosticism, is that the difficulty of explaining why an all-powerful, all-loving God would allow suffering in the world. And a lot of people get very much stymied by that. Now, there's great explanations for this. You know, in chapter 6 of this book, I take a little snippet of it in about 20 pages. But essentially, I'm writing a whole book on it right now because it is such an important and vexing question. People have authentic suffering, and they just don't get why them. And so it begins by being able to see, is there any possibility for love in suffering? I don't want to get into the question in detail, but I'll just simply say 2 things. If you have an eternal perspective, in other words, if you don't believe that this life is the end of it all, and you don't believe, therefore, that there's any ultimate tragedy, truly ultimate tragedy, that can happen in this life, you know, from the vantage point of, God's mercy. If you really think that, you know, you're destined for eternity and always have been, and secondly, if you really do believe that the meaning of life is love, and you do believe that eternal love is your destiny, then at the end of the day, you can see little glimmers of why there's suffering out there in the world. There's got to be some kind of allowance for human beings to cause suffering to other human beings, right? Because if you had no possibility of causing suffering or unlove to another human being, of undoing love, then your love would not be your own. You wouldn't be free. If you had to choose only loving behaviors, because you are pre-programmed that way, If you were literally programmed to do loving things and to be nice, and you had no other choice, that would be God's love manifest in your program, but your love would not be your own. And quite frankly, life would be not worth living. I want my love to be my own. I do not want it programmed. It's the one thing that constitutes me. The natural disaster thing, it's a whole other very long explanation, but aside, just look at it this way. If God had made everyone into a perfect world, do you think you would be really happy? Do you think you would be happy if there was nothing you could do to make the world a better place? If there was nothing you could do to actually help constitute the kingdom of God by your action? Do you think you'd be true? If we were all perfect beings and we didn't need one another one whit, and all we could do was get into competitions with one another to show how our perfection was better than everybody else's perfection, because there was no possibility or moment of compassion, because everyone was self-sufficient, and everyone was beautiful, and everyone was athletic, not like me, and everybody was da-da-da-da-da-da. Do you really think you'd be happy? You know, in a community, quote unquote, scare quotes, like that. And the point I'd say is, it's getting to the point of looking at love and suffering as not only being compatible, but suffering being ingredient to love, and suffering being ingredient to our doing something to make the world a better place, and suffering being ingredient to calling us out of the most superficial meanings of our lives to the most profound ones. And frankly, suffering and love, they're right hand in hand. I want my love to be my own. So, we all have the capacity of doing evil or suffering, causing evil or suffering to somebody else. So that's the really short answer. Maybe there's something in that. And maybe, in a sense, I have a great deal of compassion. I think he's a very authentic guy myself. I think he's struggling with questions at this point in his life that are not physics. Not physics. So
another question in the balcony.
Yeah. I was just wondering, for all the people that don't really get this, the math parts of it, for oscillation theory, isn't there a blue or red shift that has been detected that suggests that the expansion is slowing? And in other words, so that would mean that the G-force could cause re-collapse and successive oscillation?
yeah, there was a slowing of the universe up until the universe reached 0.5 redshifts, which probably occurred about 4 billion years ago. Today, the vast majority of physicists think because of the higher proportion of dark energy to dark matter, they think the universe is again in an accelerating phase, and there's actually direct physical evidence of that fact. So quite frankly, the answer is yes. For about 9 billion years, there was a gradual slowing of the universe. But then as the universe reached a size, you know, gravity becomes less and less and less effective as the gravitational bodies move away from each other. So the key thing, of course, is when the universe reaches a particular size, you know, then all of a sudden the dark energy becomes proportionately much stronger to even the dark matter plus the visible matter. And so what you wind up having at 0.5 redshifts is somewhere in the neighborhood of maybe 10 billion, after 9 billion years, you had a re-acceleration of the universe. So it would seem like that very effect would occur in previous cycles. It's a really good question. But in other words, no, it's not going to collapse. Yeah.
Over here.
Would that have had any effect, the slowing of the redshift had any effect on the constant of the speed of light?
No. Constant is a constant. We'll talk about constants tomorrow night a lot, to the point of being nauseating. But the point is, though, it's a good question, but a constant's a constant. And the interesting thing about the light constant in particular is you can't slow light down and you can't speed it up. You can launch it from any source you want. So if you have a source that launches the light, and that's going 0.9 the speed of light, and then you launch your light wave, you know what? That light wave will travel at 186,200 miles per second, or 300,000 kilometers per second. But the frequency of the light will increase dramatically. In other words, a frequency is kind of the intensity of the light, the number of light waves that pass a particular point. So ultraviolet light is the kind that burns you, right? You get a sunburn from it, or, you know. So it's blue light. Violet is violent. So just, right? So what you have then is you launch that light from a very fast moving source that's coming towards you. You're going to get what's called a radical blue shift toward the blue end of the spectrum, higher and higher frequency of the light. Or if the source is moving away from you, okay, the light, you don't slow the light down, actually. What winds up happening is it causes a red shift. In other words, the frequency of the light, now you've got, instead of high frequency sunburn light, you got infrared light, right? The old slow moving, easy going stuff that night vision goggles are made from, right? And these kinds of light waves, they can't do anything to you. You know, they won't even tan a Hawaiian. So, I mean, the thing is, you know, at the end of the day, all you can do is change the frequency of the light. You cannot accelerate the light or decelerate the light. But it's a great question.
Question back in the back. Oh, over here. Sorry.
Oh, sorry. Yes.
Is probability really good enough for me to believe in something as profound and awesome as a theistic God? Or should I demand absolute proof?
Well, I think there's a point at which I'm just going to call it faith. I mean, I don't know. I mean, you can get some very good deductive proofs, and you can see that there's a nice preponderance of evidence from physics here. But I would say that at the end of the day, what's really going to move you or not move you is when you come to what you can get from a kind of evidence like this, or from a theistic proof, is you can see two things. Number one, that there's absolutely no reason why you shouldn't believe, you know, that faith and reason are completely compatible. And number two, there's an awful lot of evidence pointing to the fact that there has to be this kind of transcendent cause outside of universal or multiversal space-time asymmetry. Now, you look at that and you go, okay, well, is that good enough? No, because that kind of a God is, you know, a kind of a, what I call a so what God, you know, in the sense of, okay, you're big, you're a creator, you could do some real thing, you could fry me, you know, I mean, you could do whatever, right, you know, you could say that, and you could say there's relevance here. But what you have to do is move to the point of what I call providence. Does God actually care about you? Does God actually love you? Does God actually redeem your suffering? Hear your prayers, answer your prayers, guide you, inspire you. Now, you can use your physics proof for showing that there's something out, maybe highly probable out there that does this. But at the same time, have you ever had this kind of intuition that sometimes you think, gosh, I am being guided from one thing to the next, and I am so lucky I didn't take that road or that road. I mean, when I was a kid, oh God, you know, I mean, I look at this stuff and I go, okay, all right, maybe it's all coincidence. And then sometimes, you know, you're writing a book and you come up with an idea and you go, is my subconscious really that smart? You know, or you just, and all of a sudden you begin to pile on these coincidences. And then you get to the biggest mystery of all, another human person. And you begin to see that that other human person, there's something uniquely lovable and good about that person. And you begin to extrapolate from that unique goodness to the sense that anyone who could be that good and that uniquely lovable, you know, do I believe that this happened through a random set of collisions I'll get to that tomorrow night, but do I really believe that this could happen over 13.7 billion measly years? And the answer is, I don't believe it. I think, that the truth of the Bible saying we're made in the image of God, I just find this truth to be blasting off the page when, like Gerard Manley Hopkins, you look into the eyes of another human being, and as he says, you see Christ playing in eyes and limbs not his to the Father through the features of people's faces. I think there's something utterly mysterious. I think there's a huge intuition, and what it comes down to at the end of the day, people say, oh, you're just wishful thinking. Oh gosh, I've heard that thing so many times. I've got more of a skeptic's gene than anyone in this room. But, hence, as my mother always used to say, why are you always working on your numbers? She just, what's the matter with you? And of course, my thought was, well, I got the gene. I want to make sure, but I always discovered I could never be sure. I just kind of looked around me at a certain juncture, and I affirmed that love was the meaning of life. I affirmed that faith and reason were coincident. I affirmed that there was lots of evidence for the existence of a transcendent deity. And I reasoned to myself that anything as good as a human being when they're loving nicely, that anything as good as human beings when they are truly good. Do I really believe that this was as it were, a chance occurrence? No, but more than that, it's the intuition of the moment, of actually moving from the mystery of the other to the mystery of God. There's another fellow, John Henry Newman, that I quoted at the very beginning, and he had a kind of another approach. He went from his conscience to God. There's a lot of other people who've done this intersubjective thing, but I think we all do it. I don't think we just believe in God because it's proven. I think there's something inside of us that says, I think there's something absolutely right about this. I think that the goodness about which the scriptures speak, I think it's true. I think we are made, with the dignity in the image and likeness of God. I really do think at the end of the day that if love is the meaning of life, and get this, I really think too that if it's the more powerful thing, the most powerful thing that's within us, I think that God couldn't be devoid of it. And if God couldn't be devoid of it, then there is really, truly this loving God that's out there. And if there really is even an unconditionally loving God out there, then would he come to be with us? Would he want to be with us? Would he want to be Emmanuel, God with us? And then I read something like the Prodigal Son Story. And I got to tell you, I read that story, I go to myself, I say to myself, that father in that Prodigal Son story, that's what unconditional love is. That's it. And if Jesus said that's God, okay. At the end of the day, I can't prove that with physics. But I just know it to be correct. If love is the meaning of life, then God ought to be, supposing that God exists from all the evidence you can garner, then God at the same time would have to be unconditional love. And anyone who could say that story and mean it about God, it's okay by me, because I can't do that with physics. But something inside me just tells me it's true. And then you pray, and at the end of the day, that prayer will confirm it for you. I believe in genuine religious experience. I think I've had little glimpses and big glimpses since I was a little kid. And that's kind of my history, but that's the way I'd answer it. There's got to be some room for your own movement of the will.
Any other questions? Well, thank you very much for your attendance here tonight. Father Spitzer will be available to sign the books right here.
Sure.
So, thank you.
Great. Thank you.